This video will talk about the subtraction strategies and algorithms that we teach in 3rd grade here at Berrytown School. A quick note before I begin, all of the strategies and algorithms that I'm going to show you are for circumstances where you have at least one smaller place value in the top number than you do in the bottom number. For instance, 115 minus 87, you can see that in both the ones place and the tens place, we have a smaller value on top and a larger value that we need to subtract down at the bottom. In the event that this isn't the case, for example, with 184 minus 52, we want to make sure that students understand that you can just subtract down using place value. 4 minus 2 equals 2, 80 minus 50 equals 30, and 100 minus nothing equals 100. The answer is 132, and nothing extra needs to happen here. The other strategies and algorithms I'm going to show you right now all have to do with problems when this is not the case. Let's move over to the adding up strategy. We teach the adding up strategy to students with a number line, and we have them put both numbers on the number line and then make jumps from the smaller number towards the bigger number to find what the distance is between them. With this problem, students might start at 48 and jump 2 to get to 50. They might then jump 50 to get to 100. And then finally 23 to get to 123. Now students have to add these jumps up to figure out the answer. 50 plus 23 equals 73, and 73 plus 2 equals 75. The answer is 75. Once we teach students to do this on the number line, we encourage them to see these jumps away from the number line just using number sentences. You can see I've written out this problem below just using number sentences. The first thing we did up on the number line was we jumped 2 from 48, and you can see I've reflected that in the number sentence down here. Our second jump was a jump from 50 plus 50 to 100, and then the last one was 100 plus 23 got to 123, and students find their answer in the middle of all those number sentences. It's all the jumps that we made on the number line. Students might choose to make different jumps on the number line or in their head, and that's encouraged. What you want to look for are that students are making efficient jumps, so chunking large groups of that distance in one shot. Students who jump from 48 to 50 and then go 10 to 60, 10 to 70, 10 to 80 are encouraged to try and make those jumps in bigger groups of 10s, maybe 20s, 30s, 40s, and so forth. Students using the added up strategy for this problem might also know that they can get from 48 to 100 with a jump of 52, and that again is okay and encouraged. Let's go take a look at the regrouping algorithm. The regrouping algorithm is what most people were taught in school as borrowing. When we teach regrouping, we're going to use expanded notation to help students understand what's happening with the place value. So our problem remains 123 minus 48, and what I'm going to do is I'm going to break that out into expanded notation, which would look like this. 100 plus 20 plus 3 minus 40 plus 8. You can see what I've done is I've taken my numbers and broken them out into their place values so that I can manipulate them and see what each digit actually stands for. In order for students to master the regrouping algorithm, it's important for them to have a strong understanding of our place value system. One idea that I like to stress with students when teaching them this algorithm is that the top number, 123, doesn't change when we use this algorithm. We're simply calling 123 by a different name. Let me show you what I mean. When we look to do 3 minus 8, we know that that would get us a negative number. And so we need more ones in the one place. So what I'm going to do is I'm going to take this idea of 23 here, and I'm going to regroup it so that it looks differently. instead of 20 and 3, I want to have 10 and 13. You can see that I've taken one of my groups of 10 and turned them into 10 ones. My number still remains 100 plus 10, 110, plus 13, which is 123. And I like to have students prove to me how they still have 123 after they've regrouped. Now, 13 minus 8 doesn't get me a negative number. 13 minus 8 equals 5. When we look at the tens place, we see 10 minus 40 would get me a negative number, and so I need more tens in the tens place. What I'm going to do is I'm going to take my 100, and instead of having it be 100 and 110, what I'm going to do is I'm going to make it 11 tens, or 110 in the tens place. Again, I'll have students show me where we still have 123. My 11 tens and 13 ones add up to 123. I haven't changed this top number at all. I've simply called it by different names. Now, 110 minus 40 doesn't get me a negative number. That gets me 70. The answer to this problem is 75. Once students are used to using this algorithm with expanded notation, we'll go ahead and show them how to do this algorithm with standard notation. The same ideas apply. 3 minus 8 would get us a negative number. So, I'm going to take this 20, and instead of calling it 2 tens, I'll call it 110, and move the other 10 into the ones place, leaving me 13 ones. 13 minus 8 equals 5. 10 minus 40 would get me a negative number. So I'm going to take this 100 and instead regroup it into 10 tens, leaving me 11 tens, or 110 as my value in the tens place. 110 minus 40 equals 70. The answer is 75. Next, let's look at partial differences. In partial differences, we don't regroup the top number, and instead, we just keep track of whether each place value is in the positive or the negative. Just like when we taught regrouping, we're going to teach partial differences using expanded notation as well, so students can understand what exactly is happening with each place value. So, 100 plus 20 plus 3 minus 40 plus 8. Now, when we did regrouping, we looked at 3 minus 8 and we said we needed more in the ones column in order to subtract, and so we regrouped that 20 and brought 10 over to the ones. This left us with extra in the ones column. We had some left over. When we do partial differences, we're not going to regroup. Instead, we're going to keep track of how much we're short or how much we have left over with each place value. For instance, 3 minus 8 is negative 5. Or, the way we'd explain it to kids, we are short 5 in order to break even here. When we did regrouping, we brought 10 over, but we don't need a whole 10. What we really need here is 5, and so we do negative 5 and take that 5 away at the end. The same will apply now when we go to the tens column. 20 minus 40 means we're short by 20. When we regrouped this 100 and brought it over to the tens place, we actually brought over way more tens than we needed in order to subtract. Really, what we need here are 2 more tens, or 20 minus 40 equals negative 20. Now, 100 minus 0 equals a positive 100, and to solve, all you do is put this number back together. 100 minus 20 equals 80. And 80 minus 5 equals 75. Just like with regrouping, once students have mastered doing partial differences and expanded notation, we'll have them go ahead and do it with standard notation. The only difference between moving to this step and regrouping and partial differences is that we're going to keep the answer with partial differences in expanded notation, even though we're starting with standard notation. Let me show you what I mean. 3 minus 8 equals negative 5. 20 minus 40 equals negative 20. And 100 minus 0 equals positive 100. Even though I'm using standard notation up top, I want to use expanded notation down below so that I'm making sure that I account for the value of each place value. So 100 minus 20 equals 80, and 80 minus 5 equals 75. That's how you do the partial differences algorithm. The last strategy I'm going to show is called Make It Friendly. And this is different than all the others because everything else I've shown so far has a sort of procedure that you can take to go through it. And Make It Friendly really means use solid number sense to make the problem easier for you. This is all rooted in an understanding that a subtraction problem can be modeled as the distance between the two numbers on a number line. And if you can translate this distance, meaning keep the same space between numbers but move it to two different points on the number line, or if you can manipulate that distance by making it bigger or smaller by any given amount, that can help you solve a subtraction problem. Let's take a look at one example. So we're looking at the problem 52 minus 18. Well, somebody might be able to look at this problem and see that if we adjust these numbers, if we move both numbers up by 2, that will get us to 20 and 54 on the number line. You can see that the amount that we're jumping on the number line hasn't changed, but the numbers, 54 minus 20, might be easier to subtract now. 4 minus 0 equals 4, and 50 minus 20 equals 30. If you have the ability to look at that distance and know that it's the same as 52 minus 18, you can do the easier problem and know that the answer to 52 minus 18 is 34. Let's look at Make It Friendly done a different way. Here we're looking at the problem 96 minus 48. Now, instead of keeping the same distance the way we did the last time, we're going to look at manipulating the distance to make the numbers a little bit more friendly. For instance, I could look at these numbers and know that from 48 to 98 is a jump of 50. And so therefore, to do my original problem of 48 to 96, it must be a jump of 2 less than the jump of 48 to 98, or a jump of 48. Let's look at doing Make It Friendly a different way. We'll use the same problem, 96 minus 48. And I'll go ahead and set up my number line. This time, though, I'm going to use my knowledge of hundreds partners. I know that it takes 52 jumps to get to 100 from 48. And if that jump is 52, the jump from 48 to 96 must be 4 less than that jump of 52. So 52 minus 4 equals 48, and I know that my jump from 48 to 96 is a jump of 48. I hope this video has been helpful in showing you what we're doing in class. And as always, if you have any questions, please don't hesitate to get in touch. Thanks.